do this so our guest can actually see me. Good afternoon, everybody. Oh, yay, you guys are learning. That's fantastic. I'm going to try again, though. Good afternoon, everybody. Thank you very much. Good grief, this is the last day of the Science Festival. Let's keep that energy up. Good afternoon and welcome to the final lecture of the Scifest Africa high-profile lecture series. As you can see, we are joined by a very friendly-looking man. We've got Jim Green with us, who is the Director of Planetary Sciences at NASA. Jim, hello.
How you doing? Can you hear me?
Hi, we can hear you loud and clear. Jim, you might want to sort out Jim Adams when he gets back to NASA for giving you the graveyard shift.
It's all right. My pleasure.
Well, welcome. It really is such a pleasure to have you. We've had the pleasure of having Jim Adams here for a week. He was high maintenance, we won't lie, but thank you very, very much for sending him. And we've heard so many wonderful things about you, and it really is an honor for us to welcome you to the Scifest Africa program. Apparently, there is also a story about a bet between you and Jim for a steak dinner about finding life on Mars. And it sounds like he's going to be on the short end of that, and we look forward to hearing about it a little bit later. But just to introduce you to our audiences here, as you've heard, Jim Green is the Director of Planetary Sciences at NASA headquarters in Washington. Jim, what time is it there now? 6?
Just a few minutes after 7.
Okay, so, and your commute is, I imagine, a good part of an hour, if not more. So thank you very, very much for joining us so early. Jim, there's like about 400 Jims at NASA. I'm just saying, by the way, it's very confusing between all of you. But this particular Jim Green previously served as a scientist at NASA Marshall Space Flight Center, as well as Goddard Space Flight Center in Washington, which is an incredible facility. If you ever get a chance to go, please do not miss it. He has a BA in astronomy, a PhD in space physics from the University of Iowa, and is extremely well published. 110 scientific articles in refereed journals involving various aspects of magnetospheres for Jupiter and Earth, 50 technical articles on various aspects of computer networks and data systems. Apparently this man is a genius when it comes to these things. He's also received the Arthur S. Fleming Award for Outstanding Individual Performance in the federal government, and in 1996 he was awarded Japan's Kotani Prize in recognition of the international science data management activities. But I do know something else about you, Jim, which is also really interesting. Tell us about your diving experiences at NASA.
Well, indeed, at Marshall Space Flight Center, I had a wonderful opportunity to be a safety diver on a part-time basis. They would just call me when they would need me. So in 5 years, I made about 150 dives, and I had the pleasure of pushing around a lot of astronauts and engineers, and it was just like diving in a bathtub.
Okay, and this, in this buoyancy tank, what exactly is that you teach the astronauts down there?
So I'm in scuba gear, and they're in their full shuttle suit, and their air supply is from a tank on the top of the deck. And what happens, of course, is they have a mock-up of the repair or whatever it is they're planning to do. Mm-hmm. And in the water, you actually can perform that as if you were in space. It gives you a lot of the same sensations.
Well, that's incredible, and I think it was probably experience of a lifetime that you are going to remember forever. And there is a really cool photo which we might whip out later of you doing that. So, Jim, just to facilitate a little bit, what we are going to do is just to switch over to your slides, and I will be
So as you switched over to your slides, I cannot hear you. Wow. So I think we have a technical difficulty. I still can't hear you.
And
Ah, there we go.
there we go. We're back with you.
Good.
Right, Jim, so as I was saying, I'm just going to bring up your slides.
All right.
And you just let me know whenever you need me to move to the next slide.
Okay. So, all right, super. So what I'm going to talk about today are two beautiful worlds that we really don't know much about. And these two missions, the one on the left called Dawn, using ion engines, is going to go to a very beautiful object called Ceres. And the one on the right, called New Horizons, is on its way to Pluto. And so these two beautiful objects, the astronomy community currently calls them dwarf planets, are going to be unveiled for the very first time. We're going to get into orbit at Ceres, and we're going to fly through the Pluto system, and we're going to be able to compare these bodies and understand for the first time how these small bodies might fit in the origin and evolution of our solar system. And so if we go to the next slide, please. That's really where I want to start, is at the origin of the solar system. On the left, we have a simulation of dust material. And dust material actually is generated in certain stars, thrown out into the interplanetary, or rather interstellar media. And with this dust, it accumulates gas and becomes larger. And as you can see in this turbulent area, small objects can form. Now these are called planetesimals. These are the very small beginning pieces of what will become bodies like our planets. And we don't know a lot about the process that go from these small sizes up to kilometers in size, but we're doing a lot of the research in that area now. Now, when the planetesimals get big enough, they also collide and create what we call larger bodies, or protoplanets. And these are bodies for which, as the mass increases, the higher density materials like the iron and aluminum and other materials will melt and sink to the very core of the body. And we call that process differentiation, the ability of many objects colliding, heating, and then reforming into a body for which the core of that body is iron, or it's the heavier materials, and then the mantle and the crust is made up of the lighter materials. So this is how things get started. Next slide, please. And so we've done an extensive amount of modeling, and in the top panel we see the planets as they are today: Jupiter at 5 AU, Saturn at 10 AU, Uranus at 20, and Neptune at 30 AU. And an AU is short for an astronomical unit, and one astronomical unit is the distance of the Earth to the Sun. So that's kind of our yardstick. And then, of course, Pluto is beyond Neptune, beyond the 30 AU. So here's our giant planets. Our computer models, our formation models, as we run them, we can't seem to form them in these locations. We can't seem to form Jupiter at 5 and all the others out to Neptune, in addition to creating the comets. That's a real problem. And the only way we've been able to solve it is to use a couple basic principles that we have found out when we do this modeling, and that is, as our collapsing cloud accretes material, creating the planetesimals, and then the planetesimals collide and create planets, they can grow really fast if they're closer to the sun. So an idea about 15 years ago was, hey, let's see if we can form the solar system in any way. Perhaps we need to start with planetesimals and the protoplanets. at less than 15 astronomical units, and then have all the icy bodies, etc., that will eventually form comets and other types of objects like Pluto beyond that. And when we do that, it turns out we can form in about tens to hundreds of millions of years our planetary system. That's a real problem, because these planets are not in the position where they formed. So we then had to create another computer model. And so let's go to the next slide, please. And if you click once, there you go. We'll start the movie. Now this is another simulation on the left of, now that we formed our planet's interior closer together. Yeah, the movie hasn't started, unfortunately. Try it again, please.
Sure.
Maybe if you click your mouse, maybe that will start.
Okay. No, let's move.
You have to go back. Yeah, sorry.
Yeah, doesn't seem to be playing, Jim.
Okay. So let me describe what you'll see. Unfortunately, we're looking down at the solar system, and the colored rings are where all those planets are that we formed interior of 15 astronomical units.
Mm-hmm.
And something absolutely spectacular happens after about 850 million years. And that is, these planets interact with each other gravitationally, and they push themselves outward. And when they push themselves outward, all the icy bodies, that material that's the greenish material, moves inward and bombards the inner part of our solar system. So all these icy body materials come flashing inside of in the inner part of the solar system, bringing a lot of what we call volatiles and a significant amount of water. Next slide, please.
Mouse. There we go.
So this actually is a summary of what was in the movie. So here we are at the very top panel, very beginning of the solar system. Our collapsing cloud has created these planets. Also, other planets are starting to form in this area called the asteroid belt, the asteroidal material. That's all hard, rocky material. And in the outer part of that top panel, we call Kuiper belt objects. Those are all very cold, a lot of water, a lot of volatiles, ices, ammonias, etc. And then the planets interact gravitationally with each other, pushing them around. Jupiter just literally throws Saturn, Uranus, and Neptune outward to what we now know is their current position. And they're such large bodies that gravitationally all the small bits, all the asteroids and all the icy bodies then flow inward and bombard the inner part of the solar system. And then the planets over time at the bottom panel clear those areas out. And what you see now are the two bodies we call Vesta and Ceres. They're in the asteroid belt. And then in the outer part of our solar system, you have the object that we know as Pluto. And if you click again, what we want to know with Dawn is, what are these two bodies? Are they protoplanets? Are they really objects that have gotten large enough that they have a central core? Or are they Kuiper belt objects? Are they these cold bodies that started out at the beginning of our solar system well beyond Neptune and moved inward? And so the purpose of the Dawn mission is to really give us a good idea and find out what those two objects are, Vesta and Ceres. Next slide, please. So Dawn used ion engine and got to Ceres in 2011 and stayed for more than a year. These ion engines are a pretty spectacular new technology that we use. It's sort of like on Star Trek, your impulse engines. and allows us to literally move this spacecraft into a brand new orbit over time. And in fact, it changed its orbit from an orbit around the Sun to then an orbit around the body Vesta. And Vesta captured it, and we studied the Vesta object really well. Next slide, please. And this is also a movie. Let's see if we can click this. This is a beautiful body that we observed for about a year. The color on the body is indeed what we call mineralogy. It's really all about the types of material that are laying on the surface of the body. In this particular body, we studied, as I mentioned, for more than a year. What we found out is the mineralogy of the body itself is very similar, in fact, identical to certain types of meteorites that we find here on the Earth. And these meteorites are called HEDs. And the HED meteorites that we have found in Antarctica indeed appear to have come from Vesta. So this beautiful small body, it's about 500 kilometers in size, we now know has a central iron core. And the central iron core is more than 150 kilometers in size, so it's really huge. Next slide, please. Sorry we couldn't get the movie working. We were going to look at various aspects of it. But this iron core, it's 110 kilometers in radius. This is really a very old, primitive body. We now realize a lot more about the asteroid belt. The asteroid belt are really the pieces of material that, if it all came together, would have created a planet. And that makes Vesta what we call a protoplanet, one of those little seeds that it collects more and more material and grow into a planet-sized object. So what's really been puzzling that we now have figured out is why we have such a thing as the asteroid belt. Why didn't a planet form there? And we now know that Jupiter's gravity is so strong at 5 astronomical units from the Sun that it's kept these pieces in the asteroid belt apart, and no planet was created. Although we have remnants of the early formation of the solar system into these protoplanet objects that of course really give us an indication of what happened early on in the solar system. And in fact, the name of the spacecraft, Dawn, is really, it's not an acronym. You know, NASA loves acronyms. But in this case, Dawn really means it's going back to the dawn of our solar system. And the study of Vesta really proved that that was the case. Next slide, please. Well, after about a year, Dawn broke its orbit from Vesta, gradually pulling away, and started on its path to the outer part of the asteroid belt, to a place where the largest body in the asteroid belt exists, and that's called Ceres. And as you can see here, Ceres exists beyond Mars, but nowhere near where Jupiter is. But Ceres is about 2.5 astronomical units away from the Sun, and Jupiter is twice that, of course, at 5. Ceres also has this inclined orbit, so it's all about getting the Ceres at the right time for us to be able to get into orbit. Next slide, please. So Ceres, we also believe, since Vesta is a protoplanet, that it has to also be a building block. It has to be one of these building blocks that accretes more and more material and becomes a larger body. Whether, you know, as you can see how small it is, it's actually twice the size of Vesta. It's about 950 kilometers in diameter. Much smaller than the Moon, much smaller than the Earth, but indeed we anticipated it being one of the building blocks, just like Vesta. Next slide, please. But just last year, one of the really fascinating observations as we were getting closer and closer to Ceres occurred, and that's actually from the European Space Agency's Herschel Infrared Space Telescope. And they repeatedly observed water vapor coming from Vesta, actually being emitted in some sort of sporadic way. And as you can see in this artist's conception, it didn't surround the whole planet, but it's the body rather, but it seemed to be coming from certain areas or regions. Now, how they determine that, of course, is that Vesta actually spins. You know, it has a 9-hour spin period, unlike the Earth, which spins on its axis every 24 hours. Ceres does it in about 9, and so periodically, when certain longitudes line up with the Earth, as seen from the Herschel telescope, they saw these water emissions, and so these were really bizarre. Are they plumes? Are they cryovolcanoes? Which means are they volcanoes that are emitting ice and water? How does this material get lofted? And does it actually form some sort of atmosphere on Ceres? So this makes Ceres an even more mysterious body than we ever thought before. Next slide, please. So our best model of Ceres then comes down to this at the moment. It must have some sort of rocky inner core. And since it's a protoplanet, it must have in the very center mostly the heavy materials, the irons. It must have differentiated. And so with the heavy materials in the center, all the lighter materials above the rocky core, now we believe there's some sort of water ice layer. And then, of course, the crust has got to be full of asteroidal material. All the silicons and other kinds of material from the rest of the asteroid belt that also falls on the surface and coats it. So that's currently what our best model is, and that will change when we get into a really close view of Ceres over this next year. Next slide, please. So here's Dawn's approach to Ceres. So as you can see in the lower left, these tick marks are every couple days. And as we got closer and closer, Dawn was captured in orbit just a week or two ago on March 6th. And how that happened was Dawn actually flew by Ceres, turned off its ion engines, and then waited for Ceres itself to be able to grab the spacecraft and pull it into orbit. So right now it's making this long loop back to Ceres, and what we're doing is we're using the ion engines to reshape that orbit into a nice circular orbit. And it's that circular, once we get into that circular orbit in April, late April, we'll be able to sit there and watch the body every 9 hours, and we'll do that, and we'll get 3 full rotations, and we'll really study the body from about 13,000 kilometers away. Next slide, please. So this is also a movie. It tells us how we got into orbit.
No, also no luck.
Okay, so it really reviews pretty much the previous slide in a nice animated form and gives you a little bit of an idea of how and where and when we use the ion engines. You can see the satellite, and you can see this blue streak coming out behind it. And what an ion engine is we have a series a gas xenon in tanks. And that gas, what we do is ionize it. That means we pop off some electrons, and then we move it towards a grid that has a voltage on it, and that accelerates the xenon through the grid and out of the spacecraft. And that little thrust is one of the basic principles in space, and that is that for every action there's an equal and opposite reaction. So if you throw material out in space in a certain direction, you actually propel yourself in the opposite direction. And by ionizing the xenon and of course charging it up and running it through this grid, we're actually propelling ourselves in that manner. It's very slow, but it works in a wonderful way. Next slide, please. So here's the timeline of activities that's going on. And we've done everything in the green, and when you get down to the last thing, we've got captured in orbit, and right now we're really waiting for getting in a position where we can start taking what we call more op-navs, or these are operational navigation images, and we've done several of those at various distances. And you can see that the images that we've been taking, and I'll show you those here next, are at various resolutions. So as we get closer and closer to Ceres, we really have higher and higher resolution images. Now, the best images of Ceres we have are actually from the Hubble Space Telescope. And so making our images and comparing that against Hubble really tells you the fabulous power Hubble has. In other words, we have to get really up close and to Ceres before we really exceed Hubble resolution. Next slide, please. So here's actually our first op-nav image. This was done in December. It was at 1.2 million miles away. And Hubble observation is much better than this. But Ceres, of course, is on a trajectory. We needed to take a look at Ceres from the spacecraft point of view so that we knew exactly where it was. And make whatever course corrections we needed to. And that's what these operational navigation images are all about. Next slide, please. Now, by January, we actually started taking an image that was very comparable to Hubble. And so you can see the Hubble image taken more than 10 years ago on the left, and the dawn image of Ceres just taken in mid-January on the right, and they're about the same resolution. And of course, immediately what you see is this nice white spot. It's approximately in the same location. And so in the upper northern hemisphere, yep, there it is in the Ceres data, and also in the Hubble data is approximately in the same location. Their phasing isn't quite the same, but close. You also see darker regions. You see a lot of the similar features. Now that tells us that at least over the last 10 years at this resolution, the surface hasn't changed much, and so this white spot's been there for quite a while. Next slide, please. So here is our first rotational characterization movie. This was taken on February 12th. This is much better than Hubble resolution, and as you can see, this beautiful spherical body has many craters on it, but it also has a whole series of lighter regions, and in fact, several spots. There's several spots right there, and there's another large spot as it goes by us, sitting in the middle of a crater. And so this was really our first fabulous, tantalizing glimpse of Ceres. Next slide, please. Now, on February 19th, as we got very close, and many times the resolution of Hubble, we began to see this very bright white spot that we've seen before. Hubble observed it, and Dawn observed it in that comparison image. But we now are close enough to Ceres to resolve it into two bright spots. Although we haven't resolved it beyond that, it's really going to be when we get into a much closer orbit will we really be able to to see what these two bright spots are. The lighter spots are not as noticeable, but indeed they're there on the body, and they're extending over. There's two of them right there in the northern and southern hemisphere. Next slide, please. So we're going to talk now about the types of terrain that we see. These are two frames from that movie, and if you click once. Yeah, so we look at the terminator, and at the terminator, where we have the region of light and dark, we get the shadows. That really allows us to take a look at the craters and the crater walls and the density of the craters. And we can see in this northern terrain that it's heavily cratered. Now that must mean that that's the older part of the body. So as it formed quickly early on, created this crust, and then started to be bombarded as it gathered other material. It's all part of the accretion process of bringing material together. That's all about smashing things together and then having those pieces come together and forming a new body. If you click again, another really neat feature is what we call a basin. Now this looks like some region that's very different than the older cratered terrain. We would have expected maybe 100 craters in this particular area, and actually only see a handful. So what happened here? Something impacted the body, which then brought material up from underneath this crust, which filled in the crater, creating this smooth basin. And then over time, only a few other craters occurred. So it is a much younger terrain. Next slide, please, or next click. And of course, we have no idea what these two things are. And that's what is really exciting us, because there's some tantalizing hints that this is also at the same place on the body that Herschel saw the water vapor emitting from the surface of the body. Next slide, please. And in fact, when we map the two regions that Herschel saw, and that's in the upper panel, and the data is actually shown in the middle panel with the graph, etc. But when we look at the surface of Ceres, exactly as Don sees it, these two regions contain white spots. And so that really is telling us that there's some sort of evidence in this region that these white spots are connected to the emission of the water vapor. Next slide, please. So the next plan in late April, as I mentioned, was to get into orbit about 13,500 kilometers. And then as we orbit the body, and as Ceres rotates every 9 hours, we're really going to take a good look at it. We'll see a lot of the day side. We'll actually see on the night side profiles above the surface. If there's some sort of material that gets lofted, like a cryovolcano, we ought to be able to see indications of that. And so this will be an exciting set of data that's just days away from us getting our hands on it. Next slide, please. What our current plan is after we do that rotational characterization number 3, we're really going to get into a lower orbit. We're going to go to a survey orbit, and as the survey orbit shows, this is really at an altitude above the body's surface of 4,424 kilometers, and we'll stay there for several days, and then we'll go to an even lower orbit called HAMO, which is our high altitude mapping orbit, and that'll be at about 1,500 kilometers, and then we'll go to the low altitude orbit, about 850 or rather 374 kilometers off the surface. And so we're going to really get very high-resolution images of Ceres, just like we did Vesta. And we'll stay in these orbits actually until the fuel runs out, that lower altitude orbit, and the spacecraft will eventually have to be turned off. But that won't be for another 16 months. Next slide, please. So what do we think we'll find out when we get there? You know, is Ceres what we call an active body? In other words, is this body actually emitting this water vapor at these regions that we see from Earth with the fabulous telescopes like Herschel and Hubble? Is Ceres a protoplanet? Is it really one of those bodies that has a core, a mantle, a crust, and Jupiter's gravity has disrupted it from growing any bigger? Or is Ceres a new type of object that we call a Kuiper belt object? If you remember all the icy materials and the cometary materials that formed early on in our solar system beyond Neptune, during the time when the planets were rearranged and material was mixed up in the solar system, perhaps Ceres is a Kuiper belt object. Now, a Kuiper belt object, the one we know of that's very famous, is called Pluto. That's a Kuiper belt object. It exists and always has existed beyond the orbit of Neptune. And so when we go to Pluto, we're actually going to have the opportunity to compare the two and see if Vesta actually is a Kuiper belt object that has been brought inward during the time that we call the late heavy bombardment. And that's what the LHB means, the late heavy bombardment, this rearrangement of the solar system. Next slide, please. And that's really what the New Horizons mission is all about. So it's right now at the edge of what we call the Kuiper belt. This is another huge region of many smaller icy bodies. Pluto is several thousand, more than 2,000 kilometers in size, so it's much bigger than Ceres. We know the surface is ices. We also know that Pluto is big enough to maintain an atmosphere, so it has some atmospheric aspects about it that we want to study. And then this region, we believe, is maybe 55 astronomical units in terms of its total size. But we really don't know. This is a largely unexplored region, and we'll explore it for the first time with New Horizons. Next slide, please. And in fact, what do we expect to see? When we first built New Horizons, we knew of Pluto and its moon Charon, but since then, other Hubble observations have really revealed 4 other moons, making this a very complex system. Pluto and 5 moons. In fact, this little system is unlike any of the others that we have. Next slide, please. And the reason why is really shown here. What you're seeing is a series of images that New Horizons took in January. These are actually OpNav observations. And of course, it looks like they're not registered. You see Pluto at the center, and you see Charon going around Pluto, but it looks like there's a wobble. It looks like, you know, we didn't center Pluto. Well, it turns out each of these images are indeed exactly centered, and Pluto and Charon are moving around what we call a barycenter. That's the center of gravity. And that center of gravity is beyond the surface of Pluto itself. This is really a complex binary system. That's really fascinating. Now, our moon and our Earth actually move around a barycenter, a center of mass between the two of them, except that center of mass is inside the Earth. And so when we look at the Earth and the Moon, there's a little bitty wobble, but hardly perceptible, and it gives us the impression, that moons move around in nice orbits around the central body, but in reality, they all are moving around the barycenter. Next slide, please. And so these OpNav images are absolutely critical for us to be able to fly the spacecraft, as shown here, through the Pluto-Charon and other moons. In fact, the orbit is going to be between Pluto and Charon. So we have to know where Pluto and Charon are at a very high degree to be able to do this right. This is the red line shows the trajectory, and as we move through the system, and we have a complicated set of measurements we're going to make and imaging. We're going to look at everything there. We'll see Nix and Hydra and Styx and Kerberos and Charon. And of course, our objective is to really study Pluto and understand it as a brand new object in the solar system we've never been at. Next slide, please. And so with that, we will find out when we compare Pluto with Ceres, whether Ceres is a Kuiper-Belt object, and how these two bodies and what they tell us about the origin and evolution of the solar system. So with that, let me thank everyone, and if we have time for a few questions, that would be great.
Thank you very much. Round of applause, please, for Jimmy. Right, who's going to start? Because otherwise I'm going to take over. Stephen, if just a question, and I will. Jim, just let me know if you can't hear, and I'll repeat the questions for you.
Yesterday I was speaking to Jim Adams, and he said that I asked him if we could ask you a question that would stump you, and he said Jim is unstumpable. So I'm not even going to try. But he did suggest that I ask you to talk about methane rising up around Curiosity rover, why it's going up and why that's significant.
That's okay. So methane, Curiosity is sitting on Mars, and it's actually been working great for the last couple years, and it's been making measurements of the atmosphere all the time, off and on, and what it's observed most recently is methane. Now, where did the methane come from? It's in the atmosphere. It's measuring it at about 10 parts per billion. It's very trace amounts of methane. And methane's important to know because it has potentially two origins. One, it could be generated what we call abiotically, in other words, through natural processes of water and minerals in deep in the crust where it's hot, and methane gets generated and leaks through the surface. Or it can be biological. In other words, microbes emit methane. We emit methane. Life emits methane as a byproduct of our metabolism. So methane's a really great trace gas that you want to know about. Now, we've known that Mars emits methane in certain regions. One of those regions that we even see from Earth is more than 100 degrees in longitude away from Curiosity. And so these methane vents, if they emit methane and the methane rises up into the atmosphere and then is distributed over the planet, you still have to get it into the crater. You still have to get it to where Curiosity is sitting. And so there has to be some sort of downdraft. And when we do the global circulation models, the only time that happens is in the evening, where the atmosphere gets drugged down and the winds come howling down Mount Sharp and pass by Curiosity. The problem is the methane measurements made by Curiosity are all during the day. And so that means the methane must be leaking through the surface where Curiosity is currently sitting. That's pretty spectacular. That means that Mars is a very active planet. It's generating these trace gases, and it's perhaps one step closer for us to decide if Mars is actually biologically active or not, and I'm a steak dinner away from winning that one.
Next question. Yes, Doc. Go for it.
Jim, I'd like to thank you very much for a fascinating and interesting talk. And I must say, since New Horizons was launched, I think it was the fastest launch ever. I've been waiting for it to arrive at Pluto, and I think we're going to find some very exciting things. I wasn't clear, what happens afterwards? Is New Horizons going to continue into the Oort belts or not?
Yeah, that's a good question. New Horizons is on an escape trajectory. Now that means, unlike everything else, when we launch it, we launch it into an orbit. It either goes around the Earth or it goes around the Sun. Except New Horizons is moving at 14.7 kilometers per second, and that puts it on a trajectory for which the Sun's gravity will not be able to bring it back. It will actually leave the solar system. And so after it flies by Pluto, it actually is going to continue on through the Kuiper Belt. And just like Voyager 1 and Voyager 2, it eventually is going to go beyond the heliopause and in the region between the stars.
And Jim, if I can follow on with that, I mean, what about Dawn? You said you were going to switch the spacecraft off, and then what?
Well, what will happen is Dawn will eventually run out of fuel, and that's really the critical resource on the spacecraft that allows us to always position the solar array such that Dawn receives the power it needs, and without the fuel, without our ability to make those adjustments, then Dawn will start to move away from the Sun. It then will freeze. And then that typically spells the end of our electronics. So we will not have enough fuel to pull it out of orbit from Ceres. So we want to put it into an orbit at Ceres, for which it will never come down. It will stay in orbit forever.
And when you sent Dawn to Vesta, I mean, was it ever the intention that it would go to Ceres? I know that NASA, you guys plan things decades in advance. Was that always the intention?
Yeah, it was always the intention to visit both Vesta and Ceres, and that's really a spectacular concept. Our first spacecraft to really be able to visit and study in such a complete manner two of these big objects in the asteroid belt, and the ion engines are the only way that's enabled us to do that.
Okay, well, good return on taxpayers' money. Anybody else? Other questions? Yes, one in the front.
Can Jim answer the question or not? Maybe I'll stump you on this one. What actually makes those bright spots bright?
Did you hear that? What actually makes those bright spots bright?
Okay.
Do we know?
No, not really. We can speculate all we want, but we believe it's a sign of a couple things. One, it's probably fresh material. It's not been coated with little bits and pieces of the asteroid belt, which is typically darker material that's accreted to the surface of the crust. And so something has happened that connects the what we think might be is an undercrust ocean, or at least a reservoir or pocket of water that then is coming out and spewing out onto the surface, and therefore the reflectivity is so much different than the dark crustal material. But we'll find out.
Matter of time. Let's see if anybody else. Okay, Don again. Yes.
Jim, again, sorry. Two things. The asteroid belt. Now, there was a theory once that there were two massive or reasonably large planets or planetoids which might have collided, which might have caused all the asteroids and bits and pieces floating around? And the second question is, when is NASA thinking of putting another man on the moon?
Okay, that was very difficult for me to hear. Could you repeat the questions, Anna?
Just one, your first question. I've got the second one. Just the first one loudly again, please.
The first question was, there was a theory that possibly all the planetoids, the bits and pieces in the asteroid belt between Mars and Jupiter could have been caused by the collision of two planets, or planetoids. And the second question was, when are you thinking of putting another man on the moon, or men on the moon?
Okay, so the first question I believe was one of the ideas is that the asteroid belt might actually be leftover material from large protoplanets that have collided and created that material. And you know, that's what I was told in grade school, but it's wrong.
Damn it.
Yeah, darn it. It really are the little pieces that are starting that accretion process that will create a planet. And it never really took off because Jupiter kept these pieces apart. So when the planetesimals, you know, these few kilometer-sized objects collide, pieces are all over the place. Instead of accreting back, Jupiter's pulled a set of those away. And so you then get partial accretions, and you never get the big oomph that you need to really create the bigger bodies. And so the biggest they ever got were Vesta and Ceres. And those are the two big ones. Ceres being the largest object in the asteroid belt, and Vesta being the next one.
Right. And then the second question, which you know, maybe we should be asking another division of NASA, but we'll ask you anyway. When does NASA plan to send people back to the moon?
Well, our current concept is we're going to Mars. Mars is our ultimate objective in the human exploration. Right now, there are no plans to put humans down on the surface of the moon, but we're working hard to create all the tools and capability and the science and the knowledge that we need to put humans on the surface of Mars.
Okay, the moon is so last century, guys. Let's move on. Stephen, you had a question? It's been answered. All right, a question from me. New Horizons, you know, was sort of put to, bad way of saying it, but put to sleep for quite a while. What happens when these, you know, when these spacecraft, you know, are asleep? I mean, does somebody watch them? Do they just do their own thing? You know, float out there and, you know, on their way somewhere? I mean, how do you keep track of the damn things?
Well, other than dawn, you know, Kepler keeps everything moving in the direction that we can calculate.
Oh, thank goodness.
Dawn's engines has moved it around all over the place, but indeed, we turn off most of the circuits. We have a little heater that keeps things warm. We can't freeze them, or they'll never come back. The electronics can't take very low temperatures. And then basically we have a little timer that goes on, and when the timer runs out, it wakes up, looks for the Earth, and of course we're there waiting for it. And so it's always great to hear the beacon back from our spacecraft after it's woke up and wants to begin to communicate.
And so there were 7 minutes of terror for Mars. How many minutes was your terror?
Well, on Mars, it was 7. Hitting the upper atmosphere and taking 7 minutes to safely sit on the ground was really hard. And in fact, when we got notice that it hit Curiosity hit the upper atmosphere, it was already physically sitting on the ground. The light travel time was 4 or 5 minutes. Sorry, it was at least 7 or 8 minutes at the time. Yeah, so the distance to Mars is such that light travel can be as short as 4 or as long as about 22 minutes. And at the time of the landing, it was about 7 or 8.
Okay. Any more questions? Right. Jim, we'd like to say a very, very big thank you. I'd love to know what the people walking down the corridors of NASA headquarters must be thinking, that you're talking to yourself. But please send our regards to everybody at headquarters, and thank you again for coming in early to be with us today. It really is greatly appreciated. And just so you know, we're sending NASA Jim back to you, and yeah, make him behave. Thank you very, very much for your time.
You're very, very welcome.
There we go. Thank you very, very much. Let's see where we're going.